and really what wires look like at low frequency, right? I'm going to try to be very clear about this. There's some things in Dr. Wentworth's book that he doesn't really explain, and I'll do my best to do that. So, before I start, any questions or comments? Okay. Now, this is important stuff. Probably a lot more important in the long run than people think, especially the high frequency modeling of certain devices or certain components. So, for starters, when we talk about wires, this is from last time. We always assume we have a wire of a certain radius A, and the wire has a certain length L. These are simple wires. And if you take a look at that, we could go through the math on this, but you know that for this type of an arrangement, if it's a wire, it has a certain conductivity sigma that's very high. 10 to the 7th is typical 10 to the 8th. About 5 times 0.7 times 10 to the 7th, 5.8 times 10 to the 7th. 1 over ohm meters would be the units, and that would be for copper at room temperature. But there's a variety of things that can be done to change that somewhat. It's of the order, all good conductors are about 10 to the 6 kind of thing to 10 to the 8, 1 over ohm meters, or Siemens per meter type of conductivity. And if you think about it, gold, silver, copper are the three that you think of right off the bat. Aluminum is also a good conductor, not as good as copper. But there's one other thing, it's steel. Now, steel has a conductivity about 1/2 that of copper, about 1/10 that of copper, but its permeability, mu relative, for 1050 steel, is about 1,000. So that factors into a big change in the self-inductance. And these are things you just have to keep in the back of your mind when you're doing any type of engineering that involves stainless steel or steel generally. All right, so when we have this there, the first thing we look at, well, let me put down the area. Here is pi a squared, and therefore the DC resistance of wires is proportional to the length, inversely proportional to the area, and inversely proportional to sigma. And I think we covered that on Friday. And that's something that you should know pretty well because you've seen this before, right? Now, that's RAC. Next thing we always look at it, and we see, is the skin depth less than the radius of the wire? And if it is, if this is the case, and by the way, skin depth is equal to 1 over the square root of pi f mu sigma, and you have to know that. That's the skin depth. Is everybody clear on that, class? Then you have to put down RAC. This is an approximation. It's still proportional to the length, inversely proportional to sigma, but now the area changes. Technically what they'll put down, and you don't have to do this, if this is the case, you'd put down pi times quantity A squared minus A minus the skin depth squared. The pi A squared is just the area. The pi times A minus the skin depth squared is really the area of the core beneath the skin depth that you're subtracting from. And this usually approximates as L over sigma pi, and then there's going to be a factor of 2A and times the skin depth here. What this really is the perimeter's length times the thickness of the skin depth. The perimeter would be 2 pi A of a wire. That's the outside length, and it would be times the skin depth thick. Y'all follow me? That's an approximation. This is exact, but generally speaking, you usually have skin depth either much less or skin depth much greater. You don't have that gray area where you have to default to that. All right, that's for the resistance of wires. Now we talk about inductance. Of a wire. Again, length L, radius A. We have to break this down and write this down. This is internal inductance. That means how much it's associated with the energy inside the wire. I mentioned this on Friday. Now this is not the majority of the inductance in wires, usually. It is if they're parallel, like transmission lines, like extension cords. Then that inductance will be significant and may be the dominant. But generally, the magnetic energy outside the core of the wire is where all the energy is. So inside the wire, this is internal resistance. We take a look at L internal, and this would be for DC. And it's just proportional to mu over 8 pi. Now that would be per meter, so you have to multiply it by the length, and maybe I'll use small l here to designate length because capital L looks like inductance. And that would be in henries. Are you with me, class? Do you remember seeing this back in the day when you were doing your EMAG 1 stuff for magnetostatics? How many do? You do, Jack? You do? Remember, this stuff is going to stay with you for a long time. Like, unless you get into something that is just strictly chemistry or marketing, you see this all the time in designs. That's internal inductance. That's low frequency. Then, if the skin depth is less than A, we could put much less than A here. Then you would say L internal. And what I like to do is call it either AC or HF. HF is high frequency. And it's approximately mu over 8 pi. Well, that's the inductance, DC inductance, times L, and then there's a factor of 2 skin depth over the air, or over the radius A. It's in his book. I can't tell you the page number of that. I don't have my book here.
505.
It's on page 505? And what formula?
It's going to be 9.7.
And he'll have it as mu over 4 pi divided by A times the square root of pi f mu sigma, I think. He'll have a different version of this. Does it?
Let me see. Or,
just leave it there.
yeah. I think this is the one that you were just referring to.
Yeah, what he does is get rid of the 8 and cancels the 2. So it's skin depth over A and it's got the L in front. That's right.
So that's generally true for high frequency. Pardon?
What's the bottom one for? You said, what does it say right above the high frequency?
Just HF, high frequencies. This is internal, L internal. Sorry. Capital L, and it should be internal. I'm just abbreviating. Okay? Now, again, this is one of those things. Everything with inductance on wires, first you have to think about this. Everything we do, we do something in a differential mode. We send current and we receive current, right? We drive things with plus or minus voltages. We talk about power transmission. On lines, we have 3 lines, 3 different phases, but we have either the earth ground, or we have some kind of a grounded return, and we know the paths of the current. They go down one way and through the earth, basically, right back. And you understand that. Well, knowing that path gives you the ability to calculate the actual external inductance precisely. But most of the time, for instance, if I wanted to get an estimate of the internal inductance of, say, a wire I ran down there to that camera, and I had another dangling wire coming back as a ground, say for a whole bunch of stuff. Well, I would use something called a partial inductance. So these are all internal so far. This is external inductance. I'm going to make mention of something. It's everything outside where the current's flowing, internal to the wire. If you think about this logically, and a lot of people will do this. I remember when I sat where you were, and even when I was teaching this, I had these kind of questions pop into my mind. How they should think this, how would I respond to this? When you think about this, just think about a wire infinitely long with a current I. Infinitely long. This is a first order approximation of a power line. All right? Let's assume there's no return path. Well, if we come out here at a distance rho away from the center, then we know that the actual H field would be I over 2 pi rho in the A phi direction. Y'all remember that? What law allows us to get that? Does it, or either mathematically state or give me the name? Anybody? Well, there's two big laws, Gauss's law and Ampere's law. Want to take a shot now? It's one or the other. Has to do with current, probably Ampere's, right? What does Ampere's law say? The integral of h, or the line integral of h dot dl over a closed path is equal to the current penetrating that path, right? Y'all remember that? Yes. I got head shaking. Yeah, that's the exact thing. Well, if you think about, we know the h field is in the phi direction, it circulates. Take a look at the length of the path, it would be 2 pi rho, right? If I take a look at that times h, it equals total current penetrating that, which is I. I didn't worry about how it's dispersed inside that wire. Once I have h, if I multiply it by mu, I get b, right? And once I have b, now I can get something per unit length of flux linkage. Do y'all remember flux linkage, that term that Gross uses all the time? How many have had Dr. Gross in power here? Almost everybody. All right. Well, flux linkage is really, you calculate the amount of flux, and flux means an integral of v dot ds over a surface, and then divide by the current, right? And if you have more than one turn, you have to multiply by n. So if we just theoretically took a look at this, take something that's got a thickness of, or a width of 1, just call it h equal 1. And if I want to figure out the total amount of magnetic flux linked there, you're going to see how this thing blows up. Are you with me? I'm going to integrate b dot ds over that entire surface. Can you imagine this in your minds? That would be the amount of magnetic flux penetrating it. It went out to infinity, right? There's one thing you notice. What does it become? The magnetic flux per meter for an infinite wire, I'll call this Weber's actually, would be equal to mu 0 here over 2 pi, right, times the integral, and in this case it's going to go from the radius of the wire A to rho, as rho goes to infinity, of 1 over rho, right? And it's a phi, and then it's dot with the differential surface, which would be d rho dz. Since it's got a height of 1, or width of 1, I don't even put the dz. Well, that's equal to what? That's mu 0 over 2 pi, natural log of rho approaching infinity over a. What bothers you about that? You all see what I'm doing? 1 over rho integrated is natural log of rho, correct? Well, what's the problem with that? Rho is going to infinity. What's the log of infinity? Infinity, right? This approximation will break down in the limit. You can't do that. So what they do is get the h field from a limited length line. You all follow me on this? Not an infinite length, and you did this too. I'm not going to do this here because it's a little beyond what we need to talk about today. Then you find out the magnetic flux, which is finite now. And after you get that, then you take and say, well, the magnetic flux, do you all remember this? That I times inductance is equal to flux. Do you all remember that, class? So we've got flux, we can calculate inductance, right? By dividing by current causing it. And that's the way it's done. There's a lot more to this that I'm not telling you, but that's basically it. When all is said and done, this won't work. So what they came up with is kind of, it's an approximation I've never really used for any engineering work that I was paid to do, but I know it's out there, and it must be used by people, maybe in the power company. And what they do is they say, if I want the external inductance, and this is called partial inductance, so again, if I have a wire, I'm going to redraw this. Wire has a length L, right here. Permeability mu, radius A. Then I can say that L external from this formula is about 2 times 10 to the minus 7. And this is gonna be henries per meter, but it'll end up being henries, times the length of the wire, and then it will be the natural log. You can look in his book. Natural log, and what they're gonna have here is gonna be proportional to L over 2A minus 1. Better be check, I gotta check that. I don't use this very much. In your book, what formula does
This one's 9.7, the last one was
Yes,
9.7.
I'm sorry, 2L over A. Pardon.
This is 2L over A, my bad. Now, I want you to know L would be in meters, the units of this would be Henry, but the units of L would be meters. And if you look at this, at least at low, when you look at this, the real thing that tells you what goes on is this 2L over A has to be greater than 1. And if it's not, then you really don't have a wire. If you think about it, if your length is equal to the radius, you have a piece of copper, don't you? Really? Or just a chunk. It's not even worth talking about. So L is much longer than A, right here. And if you look at this, this is relatively slowly changing compared to the proportionality L. So at least in the beginning, this thing is pretty linear with L. Inductance goes up as the length. Now as you get longer and longer, then things start happening, all right? There's a little more damp, there's changes. But this is the general formula, okay? And it's in his book, he does not prove it. I never have proved this in this class, but I may. I may if time allows. So that's really inductance external to the wire, and you'll notice it's not a function of frequency. It's only a function of what? The length and the radius and the permeability. That mu, well, I'm sorry, this is external, it's assuming it's in air, I should say that. This 2 times 10 to the minus 7th actually comes out because mu is 4 pi times 10 to the minus 7th, and then it's divided by 2 pi, and you end up getting a 2 times 10 to the minus 7th out there. You don't have to worry about that. You all with me on this? That's a formula. Just understand it comes from theoretical work that's based on some approximations of straight wires. How well it works, honestly, I'm not sure. I've never used it. Everything I've done, if I need inductance, it's either measured or it uses a piece of software to do an actual solution of Maxwell's equations for the environment. Okay, now we get into real components. So we're done with wires. When we're talking about real components, we always start with resistors, capacitors, and inductors because when you took circuits, the very first things you learned to deal with were switches, inductors, capacitors, and resistors. Resistors are usually the first thing you see, and you get Ohm's law, V equals IR, and you learn how to add them in series and in parallel, and then you learn about Kirchhoff's law, and you learn about Kirchhoff's voltage laws, Kirchhoff's current law, then you learn about different methods of solving, you learn about Thevenin, all those things, but ultimately you become very familiar with circuit analysis with 3 elements, R, L's, and C's, right? I don't think you did any transistors when you did circuits, basic circuits. Did you do op-amps? You did op-amps, okay. I do op-amps when I haven't taught that thing probably 15 years, but I teach the 3810, the non-double E version of that course, and we do op-amps, but op-amps you've had, right? You find out op-amps and microcontrollers are godsends for engineers. Believe me, you want to learn to appreciate it. So now we're going to take a look at those elements you learned about, R, L's, and C's, when they're working beyond the low frequency environment. And we start first with a resistor. So this is going to be, you might want to label this as high frequency modeling. And this is going to be R, L, and C. We start with a resistor, and I want to make sure everybody's clear on this. Anytime you do a high frequency model, realize the device you're modeling looks like what it's supposed to at low frequency. What is low frequency? Start at DC, maybe a little beyond DC. Y'all with me on this? 60 hertz kind of. So when you talk about a resistor, it's always something like this, right? R. That's what it's, if you buy one of these little quarter-watt carbon tube resistors, they'll have a barcode on them, right? Those color codes, and you know how to read them. I used to have, we had, I don't know if you memorize this anymore, but you used to have to, the red, brown, black, you had to memorize the entire color schemes, number arrangement, and everything like this. Nowadays, they just print them on with that, usually. It'll say 100 K ohms or 20 ohms or whatever. You don't have to go through that barcode. The real thing you have to worry about is there's a silver or gold line at the end. Do you remember what those are? Tolerance? Gold is the good one. Just remember that. G for good. And what is that? That's less than 5%, and silver's 10%, I think, unless they've changed that. And if you want 1%, I'm not even sure how to get that anymore. That's a certain spec. Anyway, that said, that's a resistor. Could be a carbon resistor, but resistors can be anything. You can have resistors that are serpentine lines. They're nice and long because they want the resistance to be a certain value, and they just truncate them at a certain length, all right? A resistor is anything that's got a conductivity that would prevent current from flowing, and it's of a design value. Carbon are the ones you're familiar with, you break with. Now, what does a resistor look like? Always think of what it's made of. It has to have wire. Whenever you think of wire, you think of inductance. That's the way it is. So normally when they model this, they'll put a little squiggly line here, and LX. I like to say unwanted inductance. Anytime you ever use resistors in a circuit, if at all possible, keep the lead links to a minimum. The shorter the lead links, the better, for everybody's sake. Remember that. And the same with a capacitor or an inductor. You want the lead links cut down small, because that's an inductance. Now, one other thing, if you're putting current through here, you're going to get a plus to minus voltage difference, right? Anytime in the world that you have a plus to minus voltage difference, it means you have plus to minus charge separated, and you have an effective capacitance. Now, there's a lot of things I can say about this model. And this is CX. Both for capacitance and inductance is unwanted. Make sense to everybody? Does that model make sense? You're going to see this is a first order model that's used by almost everything. Some people will say, well, there might be another lead inductance here if it's a long lead. Don't worry about that. That's the essential right there. So what does this actually look like versus frequency, the impedance? So here's what we want to do. We want to figure out what this looks like. And the way we do it, we don't look at these things in terms, typically you don't look at them in terms of just linear value of Z, linear value of frequency. You take 20 times the log of resistance, this is a Bode plot, and then you plot it versus the log. It's really the paper takes the log. You know, there's 1, 10, 100, and stuff like this, all with equally partitioned distances. So when we do this, we take Z of this resistor, and this would be in dB. It would be 20 times the log. Now it's the log of the impedance. Do y'all agree that the R, this could be R, this would be S times LX would be the impedance, right? And the impedance of this right here would be 1 over SCX, right? If we used S instead of J omega. Agree, class? So if you take a look at this, it's 20 times the log. And we have this in parallel with this, right? Probably the easy way to do it is 1 over this impedance plus 1 over that impedance, 2 in series. So it's 1 over, and then it would be SCX plus, and then it's going to be 1 over R plus SL X. I'm going to drop the X in a second. I hope you realize the only thing I've done there is added the resistor and inductors, impedances in series, and I paralleled them with the capacitances impedance, right? I get that. Now I'm going to multiply top and bottom by R plus SLX. So I have 20 times the log, these are base 10 logs, and then it's going to be R plus SLX right there. over 1 plus SCX times R plus SLX. And I hope you can see the only thing I'm doing is trying to simplify. This is actually close to what Wentworth has in his book. There's nothing mysterious here, it's just plug in a chart. Now the next thing I do is I'm going to go ahead, if you look at this, if I multiply the bottom one out, right here, I get 1 plus SCXR, right there, and then I get S squared LC, CX. I'll move the R over. Are you with me, everyone? Here's a typical thing we do now. We factor out the LXCX, so really the L and the C out of the lower one, all right? So if we do that, we're going to get 1 over LXCX here. That goes away. This becomes 1 over LXCX, and this becomes R over LX. This should look vaguely familiar to something you've seen long ago when you're dealing with resonant circuits. Do y'all remember this? And if you look at this, I'm just going to ask this. What is the form of this equation? Anybody? Doesn't this look like, just the bottom part, doesn't that look like S squared plus some, I think it's zeta S, or it's 2 zeta S, I think, in your, that's not zeta, but something like that, plus 1 over what? LC. Do you all remember that one? Vaguely? That was a resonant equation, right? It was for figuring out if you had either two simple poles or complex conjugates, right? Or you could have something where you had a double pole that was considered, remember the terms underdamped, right? Critically damped and overdamped, right? That's the general form for it, right there. The actual thing that you usually get is something, write this down. And this would pertain here, you get the resonant frequency. Really what you get is called a self-resonant frequency. And what they do is, if you're talking about omega self-resonance, that would be equal to 1 over the square root of LC. This is usually omega squared right here, if you remember. Omega naught squared. Coming back to you guys, do you remember that? Resonant frequency squared. So that's the resonant self-resonant frequency in radians. The one that's probably most commonly shown is F self-resonance, and it's 1 over 2 pi square root of LX times CX. And this is just saying that I'm getting this now in hertz. That's the self-resonant frequency. You don't want to be, if you build anything and you've got a self-resonant frequency that's known, you don't ever want to operate that resistor more than 50% of the self-resonance value. For instance, if it's 10 megahertz, you don't want that resistor in a circuit where you're operating at 5 megahertz frequency components, or else you're going to have problems. This will no longer act as a resistor. Do y'all follow me in this class? So you have to understand self-resonance for operations. Now, what does this look like? Let me try to explain this my way. Whenever you see something with general like that, you know you can have simple poles, double pole, right? Or you can have complex poles. Depending on what this thing actually turns out to be, you're going to have different forms of the Bode plot. If you have a double pole, you're going to have it going down 40 dB per decade for a point. If it's just two singles separated, then it's going to be 20 and then another 20 at some point. But let me just show you the most common way they think about this for resistors. And I'll do it over here. This is called the Bode plot of it. So they take a look at it and they'll say Z here is 20 times the log. This is Z in dB. of the magnitude, and you can write all that down, but it's not necessary. Usually in Whitmore's book, he puts J omega instead of S, but either one will work. And for this one, we have 1 over Lx Cx times R plus S Lx over S squared plus R over Lx plus 1 over Lx Cx. That's the form, 20 times the log of that, and here's what it'll look like. And I'm going to put it right here. Take a look at this for a moment. Let's do it this way. So paper takes the log in this direction. This is 20 times the log of that z, magnitude of z of that. What happens is, well, when S is 0, what happens? Well, when S is 0, the impedance of a resistor is just a resistor R, right? Well, the log of R times 20 is where it starts. This would be 20 times log of just R. This is typical, by the way. I'm just telling you, this is the way, if you get parts and buy them, they'll show this. They might show the actual plot. This is much more useful. And it'll be flat. It'll just stay that way. Right? Write this down. What we're going to do is this. I'll just show you where it's going to go. It's going to start, what happens is this capacitor kicks in next. It'll be the next dominant element. And things will start falling off as 20 dB per decade. If this axis is F, not omega, then this point right here, which is called the 3 dB point, maybe the low frequency point, whatever, will be equal to one over 2 pi R times Cx. That's what this point is here. So get out of your way. Then things start going down at a rate of minus 20 dB per decade until you hit the self-resonant frequency. And F self-resonance frequency is equal to 1 over 2 pi square root of Lx Cx. That's right here. Then it will start going up, where this is now going to be plus 20 dB per decade. Like that, and it'll keep on going. Let me explain what's really going on. In his book, he'll and by the way, there's some variations. I'm trying to look at where he has that plot.
I think, yeah, one more.
This is on page 509 at the bottom. But he does an actual MATLAB plot. He doesn't do a Bode plot. I prefer Bode's. That's what you'll get. Remember, a Bode plot approximates. This actual value is at this point right here. It's 3 dB below. You follow me on that? The truth is, the actual curve will do this. And come up there. Just keep going. But Bode's are an approximation. They're very useful. That's what it'll be for almost every common resistor encountered. Which means is that at first the capacitance, the parasitic capacitance, kicks in. That's this pole right here. Starts bringing it down, and then it hits a self-resonance. It starts going up. Now, there's you know, you'll be able to say, well, Dr. Dubinsky, if I take this equation from different RLs and Cs, I don't get that. I get something that comes down here, then comes down, then goes up. Something where you get something different, slightly different. This is the way it'll be generally. All right, that's almost universally accepted for a common resistor with a given internal inductance and lead inductance and a self-capacitance. There are some exceptions, but very few. okay? I'll give you problems like this. There will be Bodie plot. There'll be things that you can actually look at a real Bodie plot and estimate things, okay? They're not in his book. Next, when I teach EMC, I go through a lot of stuff that's practical that you can use. You need me to stop there? You got it? You good? Okay? All right. The next thing we talk about it is an inductor. I'm going to leave that up here for a reason. You're going to see something that should bother you. Well, what is an inductor most? How would you describe an inductor to somebody who is a friend in, say, music? What is an inductor in a nutshell? It doesn't matter how you do it. The way I do it, it's a bunch of wire wound in a coil. That's probably the easiest, simple way to say, here's what we're talking about, is a bunch of wire wrapped in a coil that allows magnetic energy to be concentrated. That's what an inductor is. Typically, an inductor looks like this, right? Lots of coils around some kind of a center, right? So go ahead, put that. Now we're talking about inductor. Symbol for an inductor is L. So when we take a look at an inductor with an L, you know, the impedance of that at lowest frequencies is SL, is it? I mean, it's J omega L, correct? As omega goes to zero, it's zero, isn't it? That's not really true, though. There's always some measurable resistance to any wire. So normally when they do these things, they say, that's what an inductor looks like, just L like that. But there's also some sort of internal resistance the wire has. And they put that X there, Dr. Wentworth does, to say it's not wanted. We'd like to get rid of it, but it's inherent. So there's some internal inductor resistance because of the length of the wire. You can't get rid of it. And the more resistance, the worse things act like an inductor. That's the general truth. Now there's also something. If you're passing current through this, you'll develop a plus to minus voltage, right? So there's also capacitance. And it's unwanted. Now take a look at the first thing I put up. High frequency model for a resistor compared to the high frequency model of the inductor. Is there any difference? None at all. The difference is this. The relative magnitude of this resistance. Over here, it could be k ohms, 10 k ohms, a mega ohm. Over here, it might be milliohms, 1 milliohm, 2 milliohm. You all with me? 10 orders, 12 orders of magnitude difference. The capacitance on the two usually is more, I got to be careful about this on the inductor. And the reason is between each winding, every time you get one turn like this, there's shellac between or some insulation, you get a gap there. That gap has a capacitance that just spirals around the entire length of the wire. Without getting into the modeling of that, just remember this. Inductors in general have more parasitic capacitance, maybe an order of magnitude more or better than a resistor of the same dimensions. Try to remember that. I can't say that with absolute authority, but it's generally true. Now, when we look at the Bodie plot of this, we take a look at this Zn here. And since it's identical to the resistor, we get the identical form here, don't we? Difference is now the R has a sub X, and what? The L is not sub X. Do y'all follow me in this class? Right? Because L is the thing we want that. What we don't want is R and C. We don't want those. So what does the Bodie plot of this look like for standard values? Well, first, the self-resonance is always the same. For this case, F self-resonant frequency is 1 over 2 pi
square root of, now it's the real L and unwanted capacitance. That's always true. Okay? But here's the difference. Remember I had a 3 dB cut point for this thing? Oh, and then I had the actual self-resonance appear. You all remember that? You don't have a 3 dB cut point. Here's what actually happened. Oh, and this will be in his book. William, you can give me the page number for this plot. But here, we're going to have F logarithmically. And this will be 20 times the log of the impedance. Remember, the impedance is the same thing as this impedance, only now L doesn't have the sub X, R does, right? And here's the thing you do. You come right out here, wherever the frequency is, you find F, self-resonant frequency. And this is going to be 2 pi square root of L Cx right here. And here's what happens with an inductor. No matter where you start an inductor, if you start at absolute 0, it'll come in at 20 times the log of the magnitude of Rx, the parasitic resistance. It's very low. And then it's going to start going up at a rate of plus 20 dB per decade, hit until it hits self-resonance, then it falls down. It keeps going down at a rate of minus 20 dB per decade in this direction. Now here's why. For this one, at very high frequencies, this capacitor will be like a short circuit. There will be nothing to stop it. And the thing will just start looking like more and more of a short circuit. So if that's self-resonance here, and say it was at a megahertz, or maybe 10 megahertz, if you operated this thing at 5 megahertz, you'd be on the hairy edge. You'd probably have a problem too. If you come down an order of magnitude or so, you're usually okay. This is the one thing Dr. Wentworth's book does not mention. Where does this thing kick in at? And you don't worry about that. What you actually worry about is this value right here. And for that, I come over here and take a look at this equation. And when we are at resonant frequency, we know these two terms go away. Do you remember that at resonance, the S squared and 1 over square root of L, 1 over L, LXCX cancel each other? That's resonance. You follow me? At resonant frequency, I should have been an S there. Resonant frequency, you're going to have this downstairs. And you're going to have upstairs. Now you would put in S equals J omega self-resonance in there. Are you with me? I'm not going to ask you to derive this. I'm trying to do this from the position of information, so to be locked in your mind when you're doing this in the real world. Remember, at self-resonance, the S squared and the 1 over LC cancel. That's the definition of resonance. You still have that frequency. So you have to evaluate these two things at the resonant frequency. If we divide by S, right, then we get this right there. All right? Now, if you take a look at that, I'm not going to mess with this much longer. If you look at this, you get a 1 over C, and I can keep playing with this. Anyway, you can evaluate that depending on the component values. That's the value you would use to calculate this peak. You take 20 times the log of this thing at resonant frequency, which will cancel that and that. You can do the whole thing. And that will be the peak value. Now that peak value is the only thing you worry about, because you know this is 20 times the log of Rx. And if I come from the peak value, which you just calculated, you can extrapolate it 20 dB per decade to see where that line intersects that line. That's how you get that point. Don't worry about going through all the permutations of the equations. That's the easy way.
Okay? You with me on this? I don't ask for that value. I don't. I will ask for self-resonance and the relative value of distance times. But those are things your calculator does. You just make sure you plug in the right values. Or MATLAB does. All right, now the next one, the one that is different is the capacity. And I have my own take on capacitors. Capacitors come in every shape and size you can imagine. You familiar with these really small little flat mica capacitors that are like picofarads, tens of picofarads, even sub-picofarads, right? The lead length themselves can significantly change that value. Just realize that. Then you get into these huge energy storage. Well, just think about transformers. When they go from AC to DC, they use electrolytic capacitors that are filled with this goo. Right? Y'all know what electrolytic capacitors are? How many do? How many have heard the term? I gotta at least make sure you're gonna be on the same page. When they talk about electrolytic capacitors, it's something that has an internal workings that's usually in a somewhat of a goo, I like to use that term, that is polarized. So if I put a plus to minus voltage, right, all the, you would call them dipole centers, will align in a certain direction. Right? That's just the reality. Now, they don't change quickly. And if they do change, they generate a lot of heat. Keep this in mind. You don't want heat in a capacitor. They go boom. So, what they'll do is use large electrolytics after they come out typically of a full wave bridge rectifier where you get a DC voltage with a ripple. You all with me on that one? Those capacitors can charge and discharge in the current going the same way all day long. I mean, it's basically, they will allow, I should say voltage. They'll allow the polarity of the voltage to be the same, even though it varies in magnitude, it's not a problem. No problem. Now, if you take that electrolytic capacitor and you try to go from a plus minus to a plus on bottom, minus on top, then they heat up like crazy. You can't have something where the actual polarity changes like it will not work. It'll be a disaster. Either they'll blow up or the resistance will be it'll be so low that it's basically overwhelming the effects of the capacitor. There's also a danger of explosion. This I'm going to talk about from a personal experience. I worked on a railgun years ago here, and even though I didn't deal with this capacitor, they had high energy capacitors. High energy capacitors at that time were electrolytic. Since I think they have some that aren't, they're much more energy dense and lighter. Well, I'm going to say they're about 250, 300 pounds a piece. I think it was 33 millifarad, which is enormous because they could withstand 10,000 volts. That's a tremendous amount of energy. I could be wrong about this, and maybe only be 1/4 of that. Anyway, they're huge. Well, I didn't do this, thank God, but I was shown, I don't remember where I've seen this, a capacitor where, unfortunately, somebody ran the current through it the wrong way. It was like a grenade went off. The shrapnel, it can kill you if you're there. And you'll see the entire thing just blown out. Has anybody ever seen a capacitor explode, the aftermath of it? You have? Well, if you have, I don't mean mica capacitors. I'm talking about these large, and they look like they're wrapped in duct tape or something, ones. Those, when they blow up, there's all sorts of evidence of a big explosion usually. The small ones won't kill you. The big ones will. Just remember what I'm telling you. But if you want to destroy somebody's life, just change the polarity when they energize one of these capacitor pins for the power companies and stuff. You'll kill everybody in there probably. But I'm trying to encourage everybody to be very careful with electrolytic capacitors and high energy density capacitors. I'm not sure about your car what they have. I know they have lithium-ion batteries, but they do have a fair number of capacitors in there to cause timing on these hybrid vehicles and electric vehicles. I'm not really sure. All right, so what does a capacitor look like? I'm going to do it over here. This is all for what they look like at high frequencies. So a capacitor, as you might guess,
At low frequency, it looks like a capacitance. Now, think always in terms of the components you're used to. You're used to small little capacitors, right, that have short leads, less than an inch on either side, correct? And you cut them down if need, or bend them if you're doing breadboard. Well, anytime you have wire leads, you have inductance. This is C, we want C, but we get this unwanted L. And whenever we don't want something, we put a sub X. It's just the way it is. Now, unlike the other ones, there is no parasitic capacitance for the capacitor. It is the dominant capacitance. You don't have to worry about it. But there is some resistance, because anytime you have wire, you have resistance. And that's the model. 3 elements in series is what it looks like. You with me? Now when you look at that, you got R, L, and C. We know the impedance of the capacitor is 1 over CS, right? An inductor's impedance would be SLX. And a resistor is just RX. So I can say Z, and I'll put it in terms of dB, of that impedance would be equal to 20 times the log here of the magnitude but I'm going to put the SLX first, plus R, plus 1 over CS. And of course, in Dr. Ortler's book, he's going to take S and allow it to be J omega. I don't like doing that. I'm just going to do it this way. And I take one look at this, and I see, well, for a capacitor at 0 frequency, when S goes to 0, what's the value of this? 1 over 0 is infinite, correct, class? It's infinite. A capacitor, an ideal capacitor, will always come in from infinity in terms of its impedance. I got to make a comment. In truth, that's not quite right. There is some called parasitic resistance in there between the between the plus and minus plate. No matter what you do, you can't get rid of it all. So there will be some resistance, but it may be like 500 mega ohms, kind of. It's so large, we don't talk about it. You with me? All right, so it comes in at infinity. What does this thing look like right here? If we're talking about a capacitor as frequency goes to infinity. And really, the way I always do this, I take a look at the circuit. I know when frequency goes to infinity, inductors look like open circuits, right? The impedance of an inductor is SL. As S gets enormous, and impedance gets enormous, this will dominate these two impedances. It looks infinite at infinity. It looks infinite at 0, correct? So what does it look like? It's the inverse of an inductor. If we take a look at this and put F self-resonant frequency here, and that will be, as the others, 2 pi square root, and here it's going to be Lx times C. And we come up, this is going to be the value at self-resonance, it will be 20 times the log of that right here, and it will come, for a capacitor right here, it's going to come from infinity, hit this point, and then go up, and these will be plus 20 dB per decade here. This is going to be minus 20 dB per decade here. Are you with me? And the self-resonance, I didn't put that down. Well, I did there. Same in all, self-resonance. Now, what happens at resonance? Do you remember one thing that happens at resonance always? I want to go back to this one. There's one overwhelming fact you should know as electrical and computer engineers. When you talk about resonance and you have an L and a C in a circuit, LCR circuits, the capacitive reactance is identical to the inductive reactance. Do y'all hear me? Except the sign is opposite. What it really means is the reactances cancel. If I take a look at the self-resonance of this thing, it means the reactance of this and this cancel. I just have resistance. Are you with me, class? Remember that always. We talk about resonant frequency, inductive and capacitive reactances cancel in terms, they're same magnitude, opposite signs. If they're in series, and if they're in parallel, they look like an infinite value of a piece. Now, what is this point then? This point would be 20, right? Times the log of just the magnitude of R. Right there. That would be R, typically of the lead. All right? You got me on that, class? Am I over? I guess I am, sorry. Okay. You want your quiz? Come on. Sorry, Tyler. I didn't realize I was running that late. Okay, any other questions? Nothing?